We will begin our video with the definition of pi. Let us take a circle. How many of the circle's diameter is contained by its circumference is its pi. For example, if 5 diameters of a circle make up its circumference, then the circle's pi is 5. If 10 diameters of another circle make up its own circumference, then the second circle's pi is 10. Mathematically, we write it as pi of a circle equal to circumference of the circle divided by diameter of the circle. But as far as we know, all the circles in the universe have same value of pi. That is, for circles in the size of hydrogen atom and also for circles in the size of Milky Way galaxy, the value of pi is 3.141592653589793238 and so on. That is why we call pi an universal constant. But why the circumferences of all the circles in the universe have same number of their diameters in them? Each circle could have had a different value of pi of its own, but they don't. Our schools might not have taught us the reason, which we will see in this video. Take two circles of different sizes. Let the smaller one be circle 1 and the bigger one be circle 2. Similarly, the diameter, radius and circumference of these circles are denoted as d1 r1 c1 and d2 r2 c2 respectively. Draw these two circles in a common center A. Draw two straight lines from A with any angle theta to touch both the circles. Join the points B and C and also D and E where those lines touch the circle 1 and circle 2 respectively. We have got two triangles, triangle ABC and triangle ADE, where triangle ABC is inside the triangle ADE. So, AB equal to AC equal to radius of circle 1 equal to R1 and AD equal to AE equal to radius of circle 2 equal to R2. Let length of BC be S1 and length of DE be S2. Isolate the triangles ABC and ADE from the circles for further examination. Observe the triangle ABC first. We know that AB equal to AC equal to R1. Since the triangle have two equal sides, it is an isosceles triangle. Being an isosceles triangle, the two angles opposite to the equal sides are also equal. That is, angle ABC equal to angle ACB. Let us consider that angle as X. Since the sum of internal angles of a triangle is 180 degrees, angle ABC plus angle ACB plus angle BAC equal to 180 degrees. X plus theta equal to 180 degrees. 2x plus theta equal to 180 degrees. X is equal to, in brackets, 180 degrees minus theta whole divided by 2. X is equal to 90 degrees minus theta by 2. Similar reasoning shall also be applied to the triangle ADE. Angle ADE equal to angle AED. Let us consider that angle as y, which will be calculated to have same value as x, that is 90 degree minus theta by 2. Imagine a pair of parallel lines which is cut by a third line. The corresponding angles formed by the cutting line will be equal in both the parallel lines. That is, the corresponding angles are theta and theta, theta and theta, 180 minus theta and 180 minus theta, 180 minus theta and 180 minus theta. We will return back to our diagram of the two triangles. It has two straight lines, DE and BC, which is cut by a third line ABD. The corresponding angles formed by the line ABD is equal in both lines DE and BC. That is, angle ADE equal to angle ABC, which is equal to 90 minus theta by 2. So if we use our above parallel lines reasoning in reverse here, we will observe that the lines DE and BC are being parallel to each other. Next, we will divide the line AD into many segments where each segment is equal to the line AB. That is, we are dividing the length R2 into multiple segments of length R1. Let the endpoints of these segments be denoted as B1, B2, B3 and so on to Bn. So, AB plus BB1 plus B1, B2 plus B2, B3 plus ditto plus B and D, it's equal to AD, which is equal to R2. and AB equal to BB1, which is equal to B1 B2, which is equal to B2 B3, which is equal to ditto to B and D, which is equal to R1. Now let us draw a line from B parallel to CE. This line cuts DE at E1. So BE1 is parallel to CE. We have already determined that BC is parallel to DE. Since EE1 is a part of DE, BC is parallel to EE1. So in the four-sided figure, BCEE1, opposite sides are parallel to each other. That is, BE1 is parallel to CE and BC is parallel to EE1. It means BCEE1 is a parallelogram. But in a parallelogram, opposite sides are not just parallel but are also equal. So BC is equal to EE1, which is equal to length S1. Now draw a line parallel to BC from B1. Let this line cut the line BE1 at C1. So a new triangle B1 C1 has been formed. When we closely examine this new triangle B1 C1 and triangle ABC, we can observe three things. First, the length of AB and BB1 are equal to R1 because we have drawn BB1 as equal to AB. Second, BC1 is parallel to AC because BC1 is part of BE1 and AC is part of AE. However, we have drawn BE1 as parallel to AE. So BC1 is also parallel to AC. This means angle B1BC1 is equal to angle BAC. Third, B1C1 is parallel to BC because we have drawn B1C1 as parallel to BC. This means angle B1C1 is equal to angle ABC. In both triangles B1C1 and ABC, we have one side equal to each other, that is BB1 equal to AB. Along with this side, we also have two angles of that side equal to each other correspondingly, that is angle B1BC1 equal to angle BAC and angle B1C1 is equal to angle ABC. If two triangles have one side and the two angles of that side equal to each other correspondingly, then those two triangles are equal to each other. So triangle B1C1 is equal to triangle ABC. It means triangle ABC will perfectly fit on the triangle B1C1. Hence B1C1 is equal to BC is equal to S1. Let us repeat the same processes throughout the triangle ADE. If we examine closely, we can observe that for every length of R1 in the line AD, there is a corresponding length of S1 in the line DE. That is, for every length of R1 inside the length R2, there is a corresponding length of S1 inside the length S2. So, number of R1 lengths inside R2 is equal to number of S1 lengths inside S2. This is written mathematically as R2 by R1 equal to S2 by S1. Let us return back to our original diagram of the two circles. We divide those two circles into multiple sectors, each with a central angle theta. Now both circle 1 and circle 2 have two regular polygons of sides S1 and S2 respectively inside them. Number of sides of these two polygons depend upon the angle of each sector, that is theta. Each theta corresponds to one side of S1 and S2 lengths in those polygons. Hence, the number of sides of those polygons will be equal to number of thetas in the circles. That is, number of sides n is equal to 360 degrees divided by theta. We know that perimeter of a n-sided polygon will be equal to the total sum of length of all sides of the polygon. Perimeter P is equal to length of first side plus length of second side plus ditto plus length of nth side. If the polygon was a regular polygon, that is, all sides of the polygon are equal in length, then perimeter is equal to the product of number of sides of the polygon and the length of one side, that is, P equal to n into S. If we rearrange it, then S is equal to P divided by n. So, S1 is equal to P1 divided by n and S2 is equal to P2 divided by n. We also know that radius of a circle is half of its diameter, that is R equal to D by 2. So, R1 equal to D1 by 2, R2 equal to D2 by 2. We derived earlier that R2 by R1 is equal to S2 by S1. If we substitute S1, S2, R1 and R2 in that equation, then D2 by 2 divided by D1 by 2 is equal to P2 by n divided by P1 by n. That is, D2 by D1 is equal to P2 by P1. Rearranging it, we get P1 by D1 is equal to P2 by D2. That is, number of diameters of the circle 1 contained by the perimeter of the polygon 1 is equal to number of diameters of the circle 2 contained by the perimeter of the polygon 2. We have reached the final step. Let us take a circle which is inscribed with the smallest regular polygon, that is an equilateral triangle. Similarly, the circle is inscribed with square and regular polygons of 5, 6, 7, 8, 9 and 10 sides. We can observe that when number of sides are increased, the inscribed polygon is turning into the circle in which it is inscribed. Even the inscribed 10-sided regular polygon is almost fitting the circle. Now imagine the same circle inscribed with regular polygons of 100 sides, 1000 sides, a million sides, 100 million sides, a billion sides, a trillion sides, a quadrillion sides, or even more. When we increase the number of sides of the inscribed polygon forever and forever, the polygon will be turning into the circle continuously. The polygon will be as close to turning into the circle as high the number of sides of the polygon is. As the polygon is continuously turning into the circle, the polygon's perimeter will also be becoming the circumference of the circle. Mathematically, we write it as when n tends to infinity, perimeter of the inscribed polygon P is becoming the circumference of the circle C. P equal to C. The equation we derived earlier is P1 by D1 is equal to P2 by D2. Now let us continuously increase the number of sides of the inscribed polygons forever and forever. This increase in number of sides of the polygons does not affect the size of the circles. That is, D1 and D2 remains the same. However, perimeter of these polygons will be becoming the circumferences of their circles. That is, P1 equal to C1 and P2 equal to C2. When we substitute P1 and P2 in our derived equation, P1 by D1 equal to P2 by D2, it becomes C1 divided by D1 is equal to C2 divided by D2. That is, number of diameters of circle 1 contained by the circumference of the circle 1 is equal to number of diameters of the circle 2 contained by the circumference of the circle 2. However, we have defined pi as the number of diameters of a circle contained in the circumference of the circle. Hence, pi of the first circle is equal to pi of the second circle, that is pi 1 equal to pi 2. Similarly, if we draw all the circles in the universe in a common center, we can prove that pi values of all those circles are one and the same. That is, pi is a universal constant for all circles. Hence proved. Kindly like, share and subscribe the video if you liked it. I am planning to upload videos covering different subjects in the future. So kindly encourage the channel. See you next time.